DK. Thanks, DK. The only advantage to having a long bio is the chance to set up a machine while it gets read, so that was good. So I wanted to talk today about some challenges and opportunities for HPC interconnects and MPI. If you read the abstract that I put together 2 months ago or whatever, that was a very ambitious abstract that I put together. So I wanted to try to tell you a little bit more focused about what I'm going to talk about today. So the outline for this keynote, and by the way, for those of you that know me, I hate keynote talks because I'd much rather sit through a technical talk where somebody's actually done some research and done something tangible that you can actually understand. A lot of keynote talks are not that interesting because they don't really engage people like I think you should be engaged when you're giving a keynote talk. So here I am giving a keynote talk, and I hate giving keynote talks for that reason. And so I'm hoping this is actually going to be interesting, that I'll say some things that are thought-provoking that we can potentially have discussions about. So I'm hoping it'll be interactive because I hate it when people just stand up. And the last keynote I was in, let me be frank with you, was in Genoa, Italy at HPCS conference. And it was a professor who was basically trying to teach us what parallel computing was and the ways that you could program parallel computers. And I sat there for an hour and I'm like, oh my God, please don't ever give a keynote like that. So I'm gonna try not to do that. I also have to keep in mind that this is being recorded too. So here's what I put together. So I was going to talk about a talk that I gave about 7 years ago at a conference where I was trying to look at what I thought the challenges for exascale interconnects were going to be. At least from my perspective, things that I thought would be interesting for us to be looking at, some of the challenges that we were facing, and some of the interconnects research that we were doing. Paul Hargrove and I actually put together a recent talk on exascale interconnect hardware trends that we presented at the Exascale Computing Project All Hands meeting in January. And so I wanted to throw those slides up in front of you as well and give you a perspective on at least what the Exascale Computing Project view of some of the challenges for interconnects, interconnect hardware. And we talk about some of the things that will do for things like MPI and some of the software layers that are associated with the interconnects as well. Then in the abstract, I had near-term research on extensions and optimizations for MPI because the work that we're doing at Sandia, which is mostly led by Ryan Grant, who's in my department, is looking at all kinds of interesting things in the near term. One of those things that he's looking at is matching optimizations for MPI. The other thing is this strategy called find points, which is a way to address massive multi-threaded applications that want to use MPI. That work is actually going on as part of the Exascale Computing Project. There's an open MPI Exascale Computing Project that's funded out of the Software Technologies part of ECP. And then I want to talk a little bit about a new portable parallel programming model for network offloading. And this is some work that Torsten Heffler and I and Ryan Grant did last summer. Torsten visited Sandia for about 2 months last summer. And so we had some really interesting discussions about doing things for supporting network offloading, and I'm going to talk a little bit about that as well. So anyway, this is what I had planned to talk about. I started putting the slides together for this, and I realized that by the time I was done, I had 85 slides. And so, going with the fact that I hate giving keynotes and that they should not just be a death by slides, I decided I would drop out the work that we were doing that was kind of near-term stuff going on in exascale computing. And so if you're interested in that kind of stuff, I can tell you a little bit about what we're doing and give you some details. But
by matching optimizations, you mean tag matching?
Tag matching optimizations, yeah. So we're looking at things like vectors, using vectors to increase the ability to match effectively, the different processor optimizations that you can do to increase matching, the performance of matching. Things like that. Okay. All right, so this goes into my previous talk that I gave about 7 years ago, in 2010, on the challenges for high-performance networking for exascale computing. So this was an invited talk and paper that I gave at International Conference on Computer Communications and Networks. I think it was in Zurich. So this is essentially what we were looking at that time and what we thought exascale was going to be and some of the challenges that were around that. So this will give you some idea of how good I am at predicting the future as well. So if I'm not very good, you can just stop paying attention after I show these slides. So this was our slide on the potential exascale architecture targets. Now, again, this is not my data, so don't look at this slide and notice that it was way off and think that I had anything to do with predicting what the exascale hardware roadmap was going to look like. This is something that I think the DOE labs put together as a result of a workshop that we had where we talked about swim lanes and what the potential architecture targets would look like. And there's some values in there that are close to where we are and some that are far away from where we are. The first one you'll notice is far away from where we are is 2018. So we thought in 2008 that we were going to be somewhere close to having an exascale machine in 2018. We're not there. In fact, DOE actually recently pulled in the schedule for getting to exascale from 2023 to 2021. And so we're actually accelerating a little bit from what we had planned to do, but that's still 3 years later than what we were looking at in this time frame. So there's some other things here that are probably not on, but again, I had nothing to do with this one, so don't hold this one to me. MPI will likely persist in the exascale era, so I think that's still true. I don't think, especially in the DOE, we have several $1 billion of investment in modeling and simulation apps that are all dependent on an MPI, and that's not going to go away anytime soon. In fact, that's going to persist probably in the trans exascale era. We're still going to have MPI for a long time. Number of network endpoints increasing. I think that's potentially true. I think there's some. I think people were surprised by some of the systems that IBM is doing with accelerated NVIDIA processors, that the node count is not as high as people expect it to be, but I still think there's going to be an opportunity for node counts to increase. I think memory and power are still going to be dominant resources. From my perspective, those are hardware challenges first, especially in terms of what you can do to be energy efficient with systems. I think there's some interesting system software approaches that can deal with energy efficiency, but I think to the first order, it's a hardware issue. And then we started talking about things that were very specific to things like MPI. I've spent a good percentage of my research career looking at how to make MPI implementation scale to full sizes of systems, being independent of things like the number of nodes or the number of processes or number of MPI ranks, and really focusing on what you need to actually enable communications and the communication patterns that apps usually have. So I still think that's one area that we need to pay attention to. And then, of course, there are performance aspects that are continuing to be important. One of the things we were focused on when I was doing this was flow control, and I still think this is an important area. So you can argue whether or not this is, high on the list of priorities for things, but I think flow control comes down to is one of the things that we really need to focus on, continue to focus on. This goes to some of the resource allocation and management strategies that we use for network performance. The biggest issue that I have, and I'll talk some more about this, is the fact that the way resources are managed, the host resources are actually independent of what the network resources are. And so in a lot of ways, what we would like to see from flow control protocols for networks is to be able to tie the host resources into what the network resources are as well. So for example, if you have a lot of unexpected messages and you're using up a lot of unexpected message buffer space in your MPI implementation, the network should know that and start using the network flow control mechanisms that it has to actually back off on the traffic that's going into the node. Because in a lot of ways, this leads to things like explicit flow control send credit management at the application level, which I think is really inefficient. You're essentially building on top of a capability the network transport already has. Network transports typically already do flow control for network resources, so if they included the host resources into that, you could actually take advantage of that and be more efficient about the way you do things. So there's some other things in here. We actually augmented our portals API and specification to try to handle flow control specifically for things like MPI when you're running out of unexpected message buffer space and things like that. And so this was what was on my mind. And I still think that's an area that networks aren't as good at as they should be in terms of providing the right capabilities for flow control and ultimately performance. Applications must become more asynchronous. I still think this is true. I don't think we've made a lot of progress in the last 7 years, but I think there's been a lot of research on things like task-based programming models. If you look at what the DOE ECP is investing in, there's work that's going on in Legion which is a task-based programming model that came out of Stanford. There's lots of work at Los Alamos on that. If you look at what Sandia is doing, there's work in things like Dharma, which is a layer on top of task-based programming models. And so we're trying to get applications to be more asynchronous. The bulk synchronous aspect of applications, I don't think, to some extent, is not going to go away. It's an algorithmic aspect. So for example, things like 8-byte all reduces are just the way our algorithms are designed. And so even if you do have some capability for doing task-based programming models that are more asynchronous, I still think there's some fundamental things that are going to lead to some of those kind of operations that are more synchronous. But I think for the most part, we've made some progress, and we're looking at how to make some of these applications more asynchronous. Active messages is one of my favorite topics. I will probably spend a lot of time in this talk talking about active messages because the work that we did with Torsten was really kind of focused on active messages. And so I was pointing out my perspective on on active messages and some of the inefficiencies that I see around that. And then the role of runtime systems. So one of the things I pointed out in this is that I think the role of runtime systems is increasing, and I still think that's true. If you look at some of the approaches that we have to programming these complex machines, what ends up happening is that people don't, it used to be you could write an MPI code, you could run one MPI rank per core, you could put it on the machine and you would be fine. What's happening now is in the diversity of hardware that we have, heterogeneous nodes with GPUs and accelerators and many core processors, the complexity of those systems is increasing to the point where the application developer doesn't want to know all of those things. And so they want to be able to write their code in a more abstract way. They want better abstractions, and then they want something else to map that to the machine. And in a lot of cases, what that means is the runtime system has to do that mapping. And so I think that's part of the work that's going on in task-based programming models and other alternative models is, what's the runtime system capabilities? What are the runtime system technologies that we need to actually do those mappings effectively? And so there's lots of work going on in the community about that. There's a group called Hi-Hat, which is working on hierarchical tasking runtime systems. There's work on things like OCR, Open Community Runtime. A lot of that work is going on to try to understand better what those mechanisms are. To me, this is a little bit scary because you're actually you're pushing the complexity of managing the resources into a lower level where that lower level may not actually have a lot of information about what the application is trying to do. And so there's work that we've done in the past from a runtime systems point of view to try to understand that better. Since Al Maloney's here, I'll call out one of the specific things that we did as part of the Express project in DOE was look at how we could leverage some of the performance instrumentation and analysis capabilities to actually inform the runtime system better about what's going on the node. And that's one of the things that we looked at to try to handle that complexity. Resiliency will impact the network API. I think this is still an area that has some work to do. I think when I wrote this, I was thinking most about things like fault tolerance and MPI. That discussion is still going on. If you ask me about my perspective on resilience and fault tolerance for MPI, I will tell you that I want to solve the disease and not the symptoms. And I think a lot of the work that's going on is trying to solve some of the symptoms. And for example, one of the things that we really need to do to address fault tolerance and resilience in MPI is understand that it's fundamentally, when you want to look at resilience, you need something that is event-driven. You need something that is, when events like faults happen in the system, it's asynchronous. It needs to be handled in some asynchronous event-driven way. And MPI was not architected as an API or implementations to be event-driven. And that's one of the fundamental things that you need to understand better when you're trying to do fault tolerance and resilience for MPI. And so I'm happy to have discussions about that and what people think on that. But I think, again, some of the things that we're doing right now are solving some of the problems, but they're not really getting to the core issues of what MPI needs to do in terms of fault tolerance. Again, this is supposed to be interactive. If you want to discuss anything, let me know. I'm trying to be a little bit controversial. It's early in the morning. They turn the lights down for this.
In this case, I have a couple of questions. I didn't know that I want to interrupt you. So,
Sure. Feel free to interrupt me.
A couple of slides back, you had mentioned linking unexpected messages to flow control.
Yes.
So how would, let's say, flow control is more of a node level event. Unexpected messages could be process level. So for instance, between two nodes, if you have, let's say, two processes per node, process A could be receiving a lot of unexpected messages in one process, but not the other one. So
Right.
handling it at a network level, wouldn't it have, let's say, negative consequences?
So if you look at the way the transport handles unexpected messages, so for example, InfiniBand, right? If you don't have resources posted to the network, the transport layer will stop. It will go back to the source and say, hey, you need to slow down, you need to stop, you need to back off, and there'll be some back off capability.
So you are more talking about a per QP level or per endpoint level.
Right. What I'm talking about is when you start running out of buffer space in the application, it would be nice if the transport actually provided a mechanism that you could actually, tap into that says, hey, the host resources are running out, as well. To the network, it shouldn't make any difference whether it's host resources or transport resources, right? There's a mechanism there for flow control. The problem with MPI and with most of the programming models that we have for parallel systems is they're fully connected. And so when you're an MPI implementation or you're SHMEM and you start running out of host resources that are critical to make things work, who do you tell to stop sending to you? How do you tell people to do that? You're fully connected. You could broadcast, hey, everybody, don't send me anything. That seems really inefficient, really, not very performant. And so what I'm saying is there are already mechanisms for doing flow control. We should be able to tap into those at the transport layer.
So talking about resiliency, what in your view is that, so let's say currently in the community, at least in the MPI community, you have two broad models. One is the ULFM model and the other is a RDMA. Do you think either one is the way to go or neither?
So I think ULFM, if I was not being clear, is one of those things that's solving some of the problems, but I don't think it's getting to the root of the issues. And so I think it's looking at some of the fundamental things like how do we restart an application with fewer processes or fewer ranks. I think that's interesting. I think some people can do that. The challenge that they're going to have is that especially for DOE applications, the best solution is the one that requires no application modification. And that's an issue the DOE has to deal with. And so from that perspective, I think ULFM is going to have a hard time getting, I think it's going to have a hard time getting into the MPI standard. I think it's going to have some application impact and people are going to be able to demonstrate some things from it, but I don't think it's really getting to the core issues that we need to solve for making MPI. And the other issue I have is that once you solve it in MPI and then you try to apply that to other models, other message passing models, other things like SHMEM, again, if you're not solving the problem at the fundamental level, you're going to have to try to figure out, again, how do we repeat that kind of activity in these other places? And I think that's going to be a challenge as well. So even if, that's my biggest issue with solving the symptoms rather than the disease, is can I take that solution and apply it to a broad spectrum of distributed memory message passing applications? And I don't really see that happening with ULFM. The reinit, I think, is, again, it's a nice solution for applications because you've minimized the impact on the applications, and as long as it performs well, I think that's what most people care about. It's interesting that most of the work that's looking at the resilience problem, they need to understand that they're actually working on large-scale systems and extreme-scale systems because that's where the resilience problem is most visible. And that most of those extreme scale systems have infrastructure that they provide to deal with the health of the nodes and things like that. And so one of the other places I struggle is where I see people not relying on the fact that we have error notifications. We have a mechanism for doing that on most large scale systems because they have a RAS system, they have something like that. You should architect a solution that takes advantage of that because doing error detection on your own, you don't necessarily need to solve that problem. Yeah. All right, so I'm going to go, I got to start increasing my speed. So I appreciate the questions and everything like that. I'll try to give you fewer details, or else we're not going to make it through the rest of these 60 slides that I have. So one of the things we were looking at was network interface controllers. We were kind of focused on power and energy at the time. We were looking at specialized network hardware, how to do some things like virtual address translation, logical node. These are the things that we were looking at in portals, and so I wanted to emphasize in what we were doing here. I think some of this stuff is still relevant in network interface controller design. Some of this goes to what we were, the research that we're doing with Torsten as well. I think things like hardware support for thread activation on message arrival, again, this is one of those low-level hardware semantics that I think would be, that I think people have, the processor vendors have actually started to look at and do a better job of implementing. And so I think, again, this is a place where that capability and functionality has been developed. We just have to figure out a way to take advantage of it and identify the limitations in it going forward. High throughput message challenges. So I think there's been a lot in the community looking at message rate. So when we started making some of these arguments 10 or 15 years ago, the community was really focused on latency and bandwidth. And that was it. And so we tried to get any opportunity we had to actually look at things that were more than just latency and bandwidth, and one of those was message rate. We were trying to take advantage of that. And I think we've done actually a fairly good job in the community of motivating people to continually think about message rate. I know there's a lot of good work going on in the community. There's things like the OSU benchmarks that emphasize message rate as well. I think that's an important aspect because, frankly, when you start looking at things like more asynchronous programming models, bulk bandwidth is not really the issue. It's getting effective bandwidth out of what you're doing in the network, and you can get that through message rate. I'm just going to skip across some of these. Topology. So I'm not really a topology guy. If you have any discussions with me, I focus more about the fabric endpoints than I do in the topology. I threw in a slide on topology. The outcome of this was network routers must be designed to allow different topologies with the same silicon. I think we've seen in the past 7 years, vendors are doing things with large port counts on their routers. So there's high radix, allows you to build different topologies, so you're not locked into a mesh or a fat tree. You can actually configure the topology how you want it to be, dragonfly, different layers. And so I think that's actually one thing that I think has been reasonably true. So that was how am I doing on predicting exascale, what technology is going to look like? I think I was okay. B plus maybe, if anybody has any issues with that. Yeah, C? Okay. Again, it was really, an opportunity for me to talk about the things that I cared about and not necessarily what the world cares about. So let me throw out some slides on exascale interconnect trends. Many core processors, throughput optimized versus latency optimized. So if you look at this is one of the hardware things that's really kind of affecting a lot of what we do in the interconnect space and the programming model space and the application space. Throughput-oriented cores, so you don't have single-thread performance. Things like, this may be good for a progress thread for networks that don't have hardware matching. The issue is communication libraries are currently not highly threaded. This is one of the fundamental issues we've seen with the MPI implementations, is that applications go to try to integrate MPI and X, whether that's OpenMP or something else. Anything that's massively threaded trying to use MPI is running into issues. Those issues come from a lot of different places. One is things like command queue slots in the network. For example, when you have InfiniBand, a queue pair gives you access to command queue slots in the network. If you only have one of those and you've got n threads that are trying to access that thing all at the same time, you have to have some kind of serialization strategy to deal with that. And anytime you try to serialize among a lot of threads, whether it's in locking data structures in the MPI implementation or locking to get access to the command queue, inefficient. And so this is one of the, that's one of the fundamental reasons that some of the MPIs are not integrating with threads very well. There are other issues there. This was just kind of putting this out in front of the applications folks so that they're aware of what's going on. I mentioned the find points and endpoints proposals here. Endpoints is interesting, but it's going to, I don't know what the current state of it in MPI is, but it's one of those things that solves some of the issues related to threads in MPI and then creates a whole significant other sets of issues on how you scale MPI resources. And so there's a trade-off there. And people are exploring those trade-offs, and I think they need to be explored. But the other challenge that I want to put out there, and I've had these discussions with the ECP folks in our applications in the exascale computing project is, and this is a fine place to talk about it, we say to our applications developers, we don't know what the right answer is for how to integrate threads in MPI. We have a couple of proposals in the forum with find points and endpoints. So this is what we're working on. And they say, great, let us know when you figure out what it is, and we'll use it. and I say, it doesn't work that way. We actually need the applications to help us understand what the trade-offs are. We need the applications to go modify their code to help us figure out what the right solution is. And to be honest with you, the applications folks are not really excited about doing that. They want sustainable solutions. They want to know that it's going to be in a standard so that they can get it from the vendors through the facilities. And so when we say to them, hey, we want to help us with these extensions figure out what the right thing is, they kind of balk at that. And so in the ECP, what we tried to say is we're going to work to get a commitment from our application partners and our vendor partners and our facilities folks so that when we do have them explore some of these techniques, they'll get some commitment that will actually sustain some of them. They may not end up in the standard in the same way with the same interface exactly, but at least over a period of time, we'll commit to supporting some of the work that you guys do from the app side. And that's an important aspect of dealing with our applications and trying to understand better some of these solutions. Talked a little bit about the overhead of tag matching and the trend to offload more processing. And so, the advice to apps folks was that future processors are likely going to continue to be a mix of these locks and talks. Big, little kinds of things are going to be out there, so be prepared for that. Things like diminishing memory footprint per core, diminishing memory bandwidth per core. These are all things that lead us to look at what the programming model is and how to deal with it. Increasing number of network endpoints per node. Again, when you take applications that were designed to do MPI everywhere and you put a 240 core processor in front of them, their first instinct is to put a rank on every one of those cores. And so we're trying to point out to them that's got some issues that they should pay attention to if they haven't figured that out already. And again, things like more network context to avoid serialization of requests. So, from my perspective, the biggest issue, and I think I have another bullet point on this later on in the talk, is if you're going to have lots of compute threads, if you're going to have lots of parallelization in the compute engine, you need sufficient parallelization in the network interface to actually support that. What's the right ratio of cores to network contexts? For me, as a guy who cares about network performance, 1-to-1 sounds good to start with. For every compute context, I want a network context. So if I'm going to have 240 hardware cores, I want 240 network contexts in my network interface to go with each one of those. So there's a trend in integrated network interfaces. So this is network interfaces moving off the I/O bus back onto the memory bus. So looking coherent like they do with all the other cores. So you're going to have a network interface that's actually coherent with the other cores. You don't have to worry about things like memory registration, the overhead of memory registration. The hardware is going to keep its cores for network activity up to date with memory maps and things like that, just as it does the cores, the compute cores. And so, most of this is going on to try to understand or try to improve the latency performance and get closer to the memory. For me, this is actually a back to the past. When large MPP systems were designed initially, guess what? The network interface was on the memory bus. It was only the move to commodity processors that put an I/O bus in the way of the network. And so we're actually going back to an architecture that we had in the past, which is really good. And then heterogeneity. You're going to have different types of cores, compute cores, whether, again, it is GPUs or many core processors. Those are going to be there. And then multi-level memory. There's an interesting, multi-level memory I think is interesting because a lot of the large systems that we're looking at procuring in the DOE, we're trying to reduce that impact as much as possible. So there's vendors that are putting high bandwidth memory on package right on the processors. And we're actually doing some things from a configuration and architecture standpoint to try to minimize the levels of memory that we have. The challenge that our application developers have is that they're developing from laptop to exascale. And so they're going to run into multi-level memory at some point along that hierarchy. And so we're trying to understand how we can have them focus on exascale where we're trying to limit essentially the number of levels of memory that we have, but they still want to be able to use commodity technology systems where that's not easy to do. Yeah.
Quick question. So you mentioned initiating communication from accelerators. So
yep.
MPI is proposing this this GPU direct async, which kind of does that.
Yep.
So do you think these kind of new solutions will require, let's say, modifications to the MPI standard as in the APIs, or would we be able to do them without like big changes to the standard itself?
Well, so I think there's two aspects to that. I don't think you'll need to change MPI to make that work effectively. There's this philosophy I have that the memory is actually the destination for messages. It's the source and destination for messages. The fact that we worry about cores is an impact of the programming model in some sense. If you look at it from a network standpoint, who cares how you initiate it? It goes from memory, comes from memory, it goes to memory. You should be able to initiate network transfers in whatever mechanism you're provided to identify the memory regions that need to be transferred. I think it's more of an aspect of how we program those accelerators than it is anything fundamental to the accelerator itself. So I think whatever mechanism you need from those accelerators to be able to make MPI work effectively need to be there, because that's probably the way that people are going to do those transfers. Now, I know NVIDIA is looking at things like SHMEM because it's a better model for them in terms of what happens at the endpoints. But I don't think it really matters in terms of what's happening at the initiator. So I don't know if that answered your question or not, but things going on in the fabric. So again, network topologies, we have increasing port counts, lower diameter networks. This is all goodness from an application perspective. You may not have to worry about topology and mapping your app to the topology as much. The issue here, and I think I pointed this out when I was talking to folks when I presented this, is that the challenge that we have in a lot of ways with things like topology is that the network is now making decisions about how to be more efficient. And so when you have the application wanting to make decisions about how to make the topology efficient, when you have the job scheduler wanting to make decisions about how to make things more efficient, and you have the network hardware trying to make things more efficient, what you end up is in a situation where somebody's made decisions about how to make things efficient, and they're not, and nobody knows who made the decision. And so, we have a lot of application folks who in the past have been worried about decomposing their application and their problem to match the network topology, who don't necessarily need to try to do that anymore. But they put some effort into that. And so, what I tell them is you have to, let go of some of this stuff and try to understand how to make the system perform best. It has to figure that out. You don't necessarily have to try that hard to figure that out. For the most part, applications people don't like that. Some of them are happy to give up that control. Others really want to understand more about what the system is doing. Offloading collective operations of switches. That was mostly motivated by the work that Mellanox has done lately. Just letting people know that the things should be more efficient because of that work. And then a couple of cross-cutting areas, non-volatile memory. So there's this trend towards network-attached storage, burst buster. I actually don't have any trouble saying that, but I can see how people have issues with that. Burst buffer. Memory pool. So there's lots of interesting work going on in the network interface community now, because people are wanting to build systems that have large pools of non-volatile memory and be able to access it over, with a load store kind of paradigm. That leads to some interesting issues with the way the network attached capabilities are. So there's still lots of work going on in that area. Power energy, the only thing we could think of from a network standpoint was being able to shut down and bring up links. There are issues with that in terms of latency to do that kind of thing, but it's something that the hardware vendors are looking at. Increasing support for inter-application communication is one of the things that I threw in there. Yeah.
So I've read reports saying that the overall contribution of network towards the energy consumption is like less than 5%.
Yeah.
So do you think this will be a significant benefit to future systems?
So I don't necessarily, so from a fabric standpoint, I don't necessarily think so. Again, I'm an endpoint guy, and so when I look at the energy efficiencies in the network, I tend to focus more on what's going on in the endpoint, which is the fact that we're moving data many times at the endpoints when we don't necessarily need to. And if data movement is an energy cost, then that's one place where we're being inefficient. To be honest with you, I don't see a significant energy savings coming from the network relative to the rest of the system.
But that's definitely an interesting point of discussion.
Yeah.
Research.
Yep. And then resilience, I think from a network perspective, resilience is actually one of the things that's always kind of been there. You're dropping packets, you're doing all kinds of stuff, and so the network support for that is pretty good. There are, again, some techniques that people are pursuing that will improve that. The issue mostly that we have with resilience is as soon as you give application developers a method of resilience that allows them to not have to change their application, that's the solution they're going to pick. And so while we develop some of these other resilient solutions and we provide support for it, again, going back to is it easier to do ULFM or just restart, applications are going to take the path of least resistance. There's a couple more things I threw in here, which were essentially weren't really part of what we presented, but that have come up recently. The convergence of network on chip with network interface controllers. So if you listen to some of the discussion that's going on in DOE right now, what you hear is processor vendors are moving towards larger network on chip networks, right? And so they're looking at different topologies for how to connect the cores and handle coherence protocols and do things like that with network on chip. A lot of this looks like what you need from a NIC for a large network, for a system level network. And so they're providing things like latency hiding with deep queues in terms of what the processor has, because they need to be able to overlap loads and stores for the network on chip. And then as soon as you put that in front of people that know anything about system networks, they say, hey, that's great, we could use some of that capability for doing load store, global load store across the entire machine. Wouldn't that be cool? We could have global load store, global shared memory, easy to program, great. I actually think the opposite is true. We have more opportunity to do things where we make the on node look more like offload, like off node, because we have a model like MPI that's not global load store, and it's not global load store for a couple of reasons. Actually, for several reasons, which is I've tried to list down at the bottom here, which is locality. So when you're doing global load store, one of the issues, again, is shared memory programming is easy. Well, it's easy, not necessarily performant. When you do load store, it leads to a lot of interesting performance issues that are mostly around locality. The reason load store, I think, is not going to work very well is because of performance portability. If you look at especially the DOE applications, again, they want to run across a myriad of systems. And so the way they run and the performance that they get is going to be determined by a lot of things. If a vendor provides us a really efficient global load store network where you can essentially use a shared memory programming paradigm, and it works really well for that one network, it's not going to get used. And we've seen this in the past. We've seen Cray systems that do this, and they're awesome. And if you're willing to port your system to the Cray and run it there and there only, you get great performance. And then Cray goes out of business trying to sell those machines because you can't support a wide set of applications. If you're not performance portable, it's not going to work. And so while I think there's interesting things that people are doing for global load store, I don't think it's going to permeate applications too much because, we are too heavily invested in MPI, and there are too many issues with how to make MPI work on a global load store machine.
Like you're implying that things around PGAS are not really going to be useful.
So my contention there is that PGAS and global load store are completely different. The kind of capability that you actually need to implement PGAS is not the same kind of capability you want from global load store. Global load store is essentially hiding the fact that you're doing network transfer. So I'm doing a load or a store to somewhere else in the network. PGAS model, and one of the reasons the PGAS model works and scales is because it's not global load store. It could potentially leverage some of that.
Would you really say PGAS model is working at scale?
Well, I think so. If I'm thinking of PGAS as something like SHMEM, and I don't see any reason a SHMEM code couldn't work at scale like an MPI code does. I don't think we have any. Again, I don't think we have any. At least the DOE doesn't have a lot of SHMEM codes, but I think there are places where SHMEM. And again, it's a fine model, it's a PGAS model, and I think it could scale just like MPI does. I think MPI RMA is part of it, is a PGAS model to some extent. And I don't see any reason why the RMA operations in MPI wouldn't scale. But I would say that there are fundamental differences between global load store and PGAS. So most pressing interconnect challenges: parallelism in the network interface, I think I've talked about, resiliency, flow control, active message semantics. I didn't leave myself a whole lot of time. I'm going to have to fly through some of the stuff that we did with Torsten, but it's around active messages. New types of communication. So I think, again, in terms of where applications are going, the fact that we're going to have runtime systems that may have to do communication, the fact that applications are getting a little bit more complex in terms of the way they do workflow and integrated analytics. And then again, I wanted to emphasize this event-driven capability. If you really look at resilience and task-based models, they really want to be event-driven. And so you want a network that actually supports that well. And MPI is an interface, and typically in terms of an implementation doesn't support that very well. And so then I've listed some other things here that I think are things that could potentially help with this situation. I'm going to just real quickly say one of the things that we're looking at is that's affecting interconnect capability and performance is the fact that applications are no longer just a single batch scheduled space shared app thrown out on a system. With exascale, people are actually looking at how to do more composition with applications. How can I put together a workflow that has multiple components? How do I get data to move between those workflow components? And so I think that's one of the things that's really going to be impacting the way that we do network programming in the future. So I just had a couple of slides that pointed out some of that. I'm going to pick on Kathy Yelick here. I hope she's not watching this video. But it was interesting for me. So Kathy gave a talk at ASCAC, which is the Oscar Advisory Council, which is DOE Office of Science. And she presented a couple of slides on what she thought was most important from a networking aspect. And so she talked about lowering overhead for small messages. Again, Kathy is spent her life doing PGAS kinds of things. And so she was looking at lightweight communication for lightweight cores. Signaling store was one of the things that she was emphasizing. So the fact that when you actually do a transfer from PGAS, it's not just a write into remote memory, because that's insufficient. That's just, you got to do more than just store it. You actually have to have some context that goes with it to tell you it's actually available there to be ready to use. And so she pointed out these things. And I sat and I was like, she's absolutely right. And I agree with everything she said. It was what she didn't say that was really surprising to me. Does anybody have any thoughts on what it is that she didn't say?
Flow control.
She didn't say flow control. That's correct. That's one of the issues. But what she didn't say was active messages. She's been an active message proponent for as long as I've known her. Everything that she's talked about to support PGAS has been active messages. Better support for active messages, how to start hardware threads when messages arrive, all the capability around active messages. And I was like, wow, this is the first time I've heard Kathy give a talk ever where she hasn't said active messages. How come she didn't say active messages? I was really surprised. One of the reasons she didn't say active messages is because there are all kinds of issues with active messages. And so Paul Hargrove has an interesting site where he's collected some issues. Paul's been working on the next generation of GasNet, GasNet EX, to look at some of these issues. Over my career, so Portals, for those of you know, I work on the Portals API. When I initially started Portals, I wanted to call it inactive messages. And I got a lot of pushback on that was politically incorrect. I shouldn't do that. And I was like, okay. But there are all kinds of issues with how you implement active messages and how they work. And the last bullet point is exactly to what you were saying, which is when active messages are essentially this idea that you have messages flying at you from all over the network, and there's a thread associated with each one of those. And so how do you schedule when you don't know what is coming? How do you schedule effectively? How do you put hardware threads to network context? How do you do all of that when you have no idea what's coming? And if you do have hardware resources where you can actually set aside those resources so that you can react to things coming from the network, what do you do when those hardware resources are exhausted? You have to fall back to flow control. And so a lot of the flow control mechanisms that you need to make things like MPI work are the same kinds of flow control resources that you need to make active messages work. And that's an interesting, there's a whole bunch of interesting issues there. Okay, so I've left myself a little bit of time to go through this, and I'm not going to be able to get through it all. But the motivation for the work that we did with Torsten was essentially looking at the fact that we have these slow cores. RDMA essentially puts, you're dumping messages from the network into memory and then letting the processors figure out what to do with those messages, right? And so what we would like to have is a situation where we can actually program the messages coming in from the network in a way that actually allows you to offload that capability. Now, offload we've done before. You know, if you look at portals, it's all about how to offload things like MPI matching and some of the other things that support MPI well. If we want to make this general purpose, which is what we were looking at, and really get active messages in a way that we really could use them. So we started looking at that. And you can look at things like, you know, if terabit networks are coming and modern processors require 15 to 20 nanoseconds to access L3 cache, then, you know, with these host processors, you have a small number of cycles where you can actually do things. For a 400 gigabit per second network, you get a 64-byte message every 1.2 nanoseconds. Where's the bottleneck there? When you're just throwing stuff blindly into memory, there's not a lot you can do with it. And so we came up with this concept of stream processing in the network, which is essentially what you can think of is something like active packets. When a packet shows up into a network interface, we want to be able to operate on that packet. And so we want to be able to do these sort of quick handler functions for packets as they come in from the network. The way we were thinking about this was the same way that we think about programming a GPU. You have compute accelerators. You have a programming model for how to program compute accelerators. What if we had network accelerators, and what would the programming model for network accelerators look like? Can we develop a programming model that is akin to something like CUDA or OpenCL, but make it work for network processors? And so we started with this idea, and then we started developing this concept where we would have handler processors, so HPUs, handler processing units, down on the NIC. You would essentially write a code at the application level that would be these small handlers. As packets arrived, then these HPUs would get scheduled to handle those packets, hopefully in you know, something like a cycle, and then you would operate on each of those packets. And then we defined the operations that you could use to do this in terms of how to move things back and forth from host memory and what the semantics of these HPUs, these handler packet units, would be. And so this is something that's not active messages, like I said. It's more like active packets. I have a header packet that arrives. I want to operate on it. And then I have a stream of payload packets that arrive. And then when all those payload packets are done, I have a completion handler that runs. And so we thought about all the ways to program this. This is a list of, again, the different handlers, some of the semantics that go along with how you schedule and run these handlers. The expectation is that we write these as standard C, C++. They're compiled by the host for a specific network instruction set architecture, so we're trying to make this as general purpose as we can. The issue, the challenge, is that in order to get line rate, you have to have very tight constraints on how these handlers run. And so we started trying to understand better the parameters that you would need to actually make these handlers run in a way that doesn't block up the network, in a way that gives you line rate performance. And so we started modeling some of this, and let me skip through some of this and get to that. What we did was this interface that we built on top of Portals, because Portals has some of the underlying infrastructure to support this. We extended the API to do this. This is all in a supercomputing paper, by the way. It'll be interesting to see how Torsten actually does a 25-minute talk based on this. I'm going to do it in 10 minutes. He's going to try to do it in 25 minutes. It'll be interesting. You guys should all show up to SC when this paper is presented and see how Torsten is able to fit all of this stuff into 25 minutes. Because if you know Torsten and his grad students, they do a lot of stuff, and they do it pretty efficiently. It's going to be hard for Torsten to talk about all of it. But basically, this is the conceptual overview of what it looks like. We have a header handler that's called once. When a header packet arrives, There's a limited amount of things that you can do. There's a shared memory region for all of the HPUs on a per message basis, so you can actually keep some state in a shared memory region that goes along with the HPUs. The payload handlers then are scheduled, and we expect packets to come in out of order. And so these packets will get scheduled onto HPUs as they come in, so you're not guaranteed that your payload's all going to arrive at the same time, so you have to write it in a way that your payload handlers can potentially run concurrently and out of order. They don't migrate, they're preemptible. And then when all the payload handlers are done, there's a completion handler that runs. So this is not unlike some of the active message implementations that have been in the past. It's just more focused on how we can program this at the network interface level and do it on a per packet basis. So these are some of the constraints that come along with HPUs and how we would expect people to program them. When you look at things like, okay, how much memory do I need to make this happen? You can fall back on things like Little's Law and look at the fact that if you have a handler that executes between 10 and 500 instructions at 2.5 gigahertz with an IPC of 1, you have a minimum delay of 200 nanoseconds per packet for a terabyte per second network. You need about 25 kilobytes of memory to actually be able to get line rate for that specific handler, which is, in today's world, that's not a lot of memory. Most network interfaces have significantly more than that on them. And so then the question is, let me get to that. The other question is how many of those HPUs you need, which I'll get to in the future. We've actually built a simulation environment to actually look at how we would do this. So it uses Torson's logopsim network simulator. It was actually coupled with Gem 5. So we use logopsim to actually simulate the network traffic where we're pulling in MPI and portals traces. Then we're coupling it with Gem 5 to handle both what an HPU would look like, to simulate that, and also simulate what the host processors would look like. And so these are the simulation settings for the network using the logp GP model, for the NIC configuration, and for the host configuration. So if you go to the paper, and I'm happy to send you a preprint copy of it for those that are interested in, you can look at the simulation settings. We modeled DMA because the only way for an HPU to do a transfer to the host is through DMA. So we modeled that. DMA is typically a high latency operation, and so again, it's preemptible. The HPUs are preemptible because the idea is that if you start up a DMA to host memory, you can probably desschedule that HPU and put something else in there while that DMA is completing. Whole bunch of results in the paper. We looked at micro benchmarks like Ping-Pong and Accumulate. We looked at them for not only comparing the way that we would do implementations for spin and comparing those to things like RDMA and portals, but also discrete NICs versus integrated NICs, because some of those settings for the simulation discrete versus integrated NICs. And of course, we have lots of results that show the performance improvement that you could potentially get for things like Ping-Pong and Accumulate when you have the ability to actually program at the NIC level. So let me skip through some of this. Things like how many HPUs are needed. So we have an analysis in the paper then. If this is something that you really want to try to build from a network interface perspective, how many of those would you actually need? And we looked at it, and it's actually a pretty modest amount, given the network's statistics that we looked at. So 8 HPUs can support any packet size if the handler takes less than 53 nanoseconds. And for 4 kilobyte packets, they have to execute in 650 nanoseconds. Again, 650 nanoseconds, when you're talking about packet processing, is actually a fairly reasonable amount of time. And 8 HPUs is not unheard of. And so then you look at, we plotted out the different ways that you could figure out how many HPUs you would actually need based on line rate and latency performance and things like that. Showed it for broadcast. The interesting thing from my perspective, let me skip through some of this, is you get to things like processing vector data types for MPI. Right? This is one of the big issues that we've had in the MPI community, is how to efficiently support non-contiguous data transfers. So strided data types and things like that. If you can handle them on a per packet basis so that you're only DMAing the blocks into memory that you really want, rather than pushing everything into host memory and letting the host deal with doing mem copies to handle non-contiguous data, that's very inefficient. And so we looked at things like that, and we measured the performance that you could get in this environment for doing things like that. And again, what you're really doing is, if you look at it, you're minimizing the amount of traffic across the bus. If you're in a discrete NIC, you're looking at minimizing the amount of memory traffic that you have if you're of an integrated NIC. And you can get real performance benefits from doing that. We did it for things like RAID. We also had another set of use cases that were around things like if you're doing key value store. If you look at what happens in a key value store right now, there's a potential for you to deposit something, on an RDMA network to support key value, where you throw a value into memory, you wait for the application to come and pick it up and look at it, and then insert it into the store. You can actually do that pretty efficiently at the network interface level. The insertion kinds of activities for most key value stores are pretty quick, and so you're wasting a lot of time pushing data into the host and waiting for the host to get scheduled, the host app to get scheduled and move that data and process it, when you can actually do things more efficiently at the network interface level. And so we feel pretty comfortable that SPIN is a way to actually get some of the active message-like semantics, but get them at a level that's actually more efficient than you would have if you just deposit messages into memory and then try to operate on them later. All right, so that was a very, again, I apologize. I left the interesting part, typical keynote talk, right? I left the interesting part really short, and I apologize for that. These are the folks that I work with at Sandia and ETH, and then some input from Paul.